Something unexpected occurred when astronomers examined the newest space imagery, forcing them to pause and take a second look. Fresh observations showed that Atlas was not acting like a silent interstellar passerby, but instead emitting two distinct jets that slowly drifted and wobbled as it traveled. These findings came from newly collected data in late December, not from recycled theories or outdated interpretations. Nothing in earlier models predicted motion this structured or this sustained. The behavior appeared deliberate rather than random. Yet, no definitive explanation has emerged. If this object is displaying activity we did not anticipate, then what exactly set it in motion as it entered our field of view? The most unsettling chapter in the story of Atlas was not defined by something it did, but by something it did not do. On December 19th, the interstellar object passed relatively close to Earth at a distance of roughly 270 million kilometers, close enough to allow astronomers to study it with uncommon clarity. For weeks, public curiosity intensified, online conversations surged, and quiet unease followed a single question. What would happen when it reached its closest approach? Nothing happened. Atlas did not decelerate, alter its course, or display any visible response to Earth's gravity or presence. There were no sudden flares, no spike in activity, and no indication that the planet beneath it mattered at all. In an era when space narratives often anticipate spectacle, this absence of reaction felt unsettling. Objects passing through planetary neighborhoods typically respond in some way, even subtly. Yet this one continued along its path as though Earth did not exist. This lack of response is significant because it removes one of the most common explanations people reach for. If the object were unstable, damaged, or strongly influenced by nearby bodies, this would have been the moment to reveal it. Instead, Atlas remained steady, preserving both its trajectory and behavior. That controlled movement made scientists hesitate, not out of fear, but because it suggested intention rather than chaos. The contrast was impossible to ignore. On one side stood rising anxiety among observers and social media voices fueled by dramatic headlines and imagination. On the other was a cosmic visitor acting with complete indifference. It neither moved toward Earth nor steered away from it. It simply passed by, silent and focused, as if its journey had nothing to do with us. This raised a deeper question about purpose and direction. Even without assuming intelligence, if Earth was irrelevant, then what was not? Astronomers began redirecting their focus away from our planet and back toward the object's broader route through the solar system. Its trajectory suggested motion with purpose, not interaction. The narrative shifted from a near encounter to a destination still ahead. Distance also shaped this moment. 168 million miles may sound vast, but on a cosmic scale, it represents a brief meeting. During that window, instruments gathered clean, uninterrupted data without sudden changes. This consistency allowed researchers to eliminate several possibilities and concentrate on long-term behavior rather than short-term reactions. In space science, silence can carry as much meaning as action. Atlas's quiet passage told observers that whatever drives it does not visibly respond to nearby worlds, that IT follows its own rules, its own schedule, and its own path through the solar system. If Earth was merely a passing marker rather than a point of interest, then where was Atlas truly headed? And why did its course appear so deliberate as it moved farther away? The defining trait of Atlas is not its shape or brightness, but its speed, because nothing previously observed has crossed the solar system quite like this. Measurements indicate the object entered our region of space, traveling at about 36 meters per second, then accelerated to nearly 42 meters per second at perihelion. For a general audience, that means it was moving faster than any known comet or asteroid ever recorded, covering immense distances in the time it takes most objects to slowly curve and drift. This extreme velocity alters how gravity influences the object. When slower visitors approach the Sun, its pull has time to bend their paths, often reshaping their orbits dramatically. With Atlas, that process barely occurred. Even after passing close to the Sun, Its trajectory changed by only about 16 degrees, a small deflection that surprised many researchers. The sun neither captured it nor meaningfully slowed or redirected it. Instead, Atlas continued forward in nearly the same direction it held before entering the inner solar system. To understand why this matters, a comparison helps. A slow-moving object behaves like a leaf floating in water, easily pushed and turned by surrounding forces. Atlas behaved more like a bullet moving through space, too fast for nearby gravity to hold for long. Gravity still acted, but the interaction window was brief, precise, and limited. That alone places this object in a rare class. Speed also limits how much information scientists can collect. High velocity shortens the time available for close observation, which is why the data gathered during its approach became so valuable. Every hour counted. Instruments had to capture details quickly because the object was already racing away almost as soon as it arrived. That urgency influenced how researchers interpreted every signal, image, and measurement. There's another reason this speed raised questions. Objects formed within a star system usually share its motion, shaped over millions of years by local gravity. Atlas did not behave that way. Its velocity suggested an origin far beyond, carrying momentum from a different stellar environment. Whatever expelled it into interstellar space did so with immense force, and that energy remained intact across unimaginable distances. This realization forced scientists to reconsider earlier assumptions. The object was not merely passing through, it was cutting through. Its motion did not adapt to its surroundings, and its path showed little negotiation with surrounding forces. That consistency made later discoveries even more striking, because any unusual behavior could not be blamed on slow chaos or random drift. In this case, speed became more than a measurement. It became a clue. It pointed to a history shaped by violent ejection, long travel, and minimal interference. It also hinted that whatever we were observing had survived conditions far more extreme than those offered by our sun. If Atlas moved through the solar system like a projectile rather than a wanderer, then how could it still produce stable structures and organized activity while racing onward? The moment scientists realized Atlas was releasing 2 jets instead of 1, the story entered unfamiliar territory. Because this behavior does not match typical comet patterns, high-resolution images revealed streams of material flowing from the nucleus in different directions, stable enough to track and active enough to evolve over time. This was not a brief eruption or a single flare. It was a sustained structure that demanded attention. Even more unexpected was the appearance of an anti-tail, a long glowing feature extending toward the sun rather than away from it. In most comet encounters, solar radiation and charged particles push dust and gas outward, creating tails that always point away from the sun. With Atlas, the opposite appeared. The anti-tail stretched more than 1 million kilometers and remained visible for months, becoming a defining feature instead of fading. This matters because temporary effects are common in space. While persistent ones are rare, a short-lived event can be explained by a sudden fracture or trapped gas release. A structure lasting weeks or months suggests balance, not disorder. Observations showed the anti-tail did not flicker unpredictably or collapse. It held its form while slowly shifting, as if guided by a consistent process rather than chance. The 2 jets added another layer of complexity. Instead of dispersing material evenly, they appeared focused and directional. Their gentle wobble matched changes in orientation, allowing scientists to link the jets to the object's rotation. This connection between movement and structure implied organization at the source, even if the mechanism remained unknown. For a general audience, the key point is not which theory explains the behavior, but why it stands out. Space is filled with ice and debris, yet most objects respond to sunlight in predictable ways. Atlas did not simply react. It maintained a configuration that resisted disruption while racing through the inner solar system. That combination of speed and stability made simple explanations harder to accept. Researchers compared the object to known comet models, and the differences kept multiplying. The anti-tail orientation, jet persistence, and long-term symmetry did not align with expectations for a fragile body breaking apart. Instead, the structure appeared maintained, as though the shaping forces were steady rather than violent. This does not mean the object is artificial, and scientists remain careful with their language. However, it does mean familiar rules no longer provide complete answers. When natural systems operate outside their usual range, they provoke new questions, not conclusions. The longer these features remained visible, the clearer it became that Atlas was not merely passing through in silence. It was actively interacting with its environment in a way not previously recorded, and it was doing so without losing its form. If two stable jets and a sun-facing anti-tail can survive under such intense conditions, then what does that reveal about the object's internal structure and rotation as it continues its journey? One of the most puzzling discoveries about Atlas is not its speed or its emissions, but its orientation in space, because its rotation axis points almost directly toward the sun. Measurements show this alignment falls within about 8 degrees, a range so narrow it immediately drew attention. In natural systems, rotation axes usually point in random directions shaped by collisions, formation history, and prolonged exposure to uneven forces. This case appears very different. To understand why, probability matters. The likelihood that an interstellar object would arrive with its spin axis nearly aligned with the sun purely by chance is extremely small. Scientists estimate it at well below 1%. In simple terms, this is not a result randomness produces often. It suggests either an unusual past or a process that keeps the object locked in this orientation. This alignment creates a strange physical condition. One side of Atlas remains in constant sunlight while the opposite stays in permanent darkness. That state is rare for small bodies moving freely through space. Most objects tumble or rotate in ways that distribute heat over time. Here, heat and energy are delivered unevenly and continuously, shaping surface activity in unexpected ways. The effects are already visible. Jets and emissions appear tied to the same regions, as if certain areas are repeatedly activated while others remain quiet. This steady exposure could explain why the activity looks organized rather than scattered. Instead of random outbursts, the object shows patterns that repeat and persist. What makes this even more surprising is the object's history. Atlas did not form under the sun's influence. It traveled through interstellar space for ages, exposed to weak radiation and long periods of cold. During that time, there was no clear force to align its rotation with our star. Yet when it arrived, the alignment was already present. Researchers have explored multiple possibilities. One idea suggests the alignment formed long before arrival, perhaps during a violent ejection from its original system. Another proposes that subtle forces acting steadily over time locked the object into this orientation as it approached the sun. Each explanation faces challenges, and none fully resolve the mystery. For a general audience, the key point is not which theory prevails, but why this detail matters. Rotation is a basic property like speed or direction. When it defies expectations, it hints at deeper structure and history. The alignment shows Atlas is not spinning randomly. Something shaped it, and that shaping left a clear mark. Scientists remain cautious. Alignment alone does not prove design or control. However, it does narrow the range of explanations that remain viable. The object's behavior now requires models capable of handling precision, persistence, and stability simultaneously. If Atlas's rotation axis is locked so tightly toward the sun, how does that orientation influence the rhythmic brightness changes observers notice next? One of the most striking signals from Atlas appeared not in its form or velocity, but in its light. Observers detected a steady rhythm repeating every 16 hours. This was not random flickering or gradual fading, but a clear brightness cycle with variations near 20%. In astronomy, such patterns demand attention because light often carries the clearest clues about internal processes. First, Some researchers proposed a simple explanation. Many objects brighten and dim as they rotate, especially if their shapes are uneven. A long or irregular body can act like a rotating mirror, reflecting more light toward Earth at certain angles. This explanation works well for asteroids and some comets, and usually accounts for repeating brightness cycles. However, this idea began to unravel as deeper image analysis became available. Data showed the bright core of Atlas contributed less than 1% of the total measured light. Even with extreme rotation, such a small source could not produce brightness changes as large as 20%. The numbers did not add up. Scientists were forced to look elsewhere for the rhythm. Instead of rotation alone, focus shifted to the material surrounding the object. Jets of gas and dust seen earlier offered another explanation. If those jets strengthened or weakened on a regular schedule, they could alter the total light without relying on shape or spin alone. To illustrate this, researchers used a simple comparison. They described the behavior like a heartbeat, where pressure builds and releases in repeating cycles. In this scenario, the object itself acts as the source, pushing material outward into a glowing cloud, then easing off, only to repeat the process hours later. Each pulse slightly thickens or thins the surrounding gas,